we're going to talk about advances in software-defined radios, taking it to the next level. What happened about an hour ago was a guy's personal experience with the start of software-defined radio. I'm going to take you quickly through the last 11 years of where SDR in the United States, in ham radio has occurred, and then I'm going to show you a glimpse of where the future. And I started doing this particular presentation, I don't know, a year and a half ago. Now the future's here, so this will be a lot of fun. The deal is, who is this guy? I'm Greg, K5GJ. I was WD0ACD for a bunch of years. I've been a ham for about 40 years. I am, when I'm not doing HF for a living, I'm a rabid microwaver. This is my 10-band rover. That's me with even less hair. That's Joe, K5FOG, my roving partner. Jim is one of our DSP and audio gurus at FlexRadio. Steve, N5AC, is also our VP of Engineering. So this is what we do when we're not playing HF. I am an electrical engineer. I've been in the industry for a while. I used to make the every other week commute to here, so I was a half-time resident of Silicon Valley. I had an office over in Scott and Central at one of the semiconductor companies, and walked in FlexRadio 5 years ago trying to sell them some microwave test equipment, and they said, "You should come to work for us." And I said, "Why should you do that? Why should I do that?" And they said, "Look, it's twice the work, half the pay. It's great. You get to work in your hobby." So anyway, that's so much for that. It's continuing to have pairing problems. So what we're going to do is talk a little bit about what makes a software-defined radio a radio. We're going to talk about the emerging system architectures, what's out there now, what's happening. We're going to talk about this direct sampling. Why is it the new buzz and the new hit? The network of things. We're going to talk about how networking, and it may not be the network you think. And signal processing and DSP, a little bit of so what and some simplicity. So first, some definitions. Audio in the back okay? Yeah. I will keep this up as long as my voice will. Software controlled versus software defined. Software controlled is where you take a PC and you attach it to radio. How many people here do HF? Oh, by the way, there'll be tests all along here. Those people that do HF with PC, how many have a PC attached to your HF radio? Yeah, half. That's software controlled radio. Even if it's a software defined radio, you're controlling it with your PC. In software defined radio, it's the modulation, demodulation, controls, and other things that are attached and being actually done by the PC, where the PC is part of the radio. And that's the key. So first, pop final on the first day of class. Is this a software defined radio? Well, let's do a little quick test. Modulation is fixed, FM only. Can we change the controls? Can I make channel and volume different? Not really. Can I change functions? Yes, I can go to repeater, I can go simplex. Is it user programmable? Yes. I'm going to stand on one foot. Anybody who has a Wouxun, wax on, wax off radio knows that without a computer cable, you cannot program those radios anymore. So they are getting tough. But you can indeed control it by software, and it does have software inside. So now I'm going to talk about this. This represents classic HF radio. I'm going to lovingly refer to these guys as Kanye Woodcraft. Okay? This is everybody's hardware-based radio. Is this a software-defined radio? Well, fixed set for modulation, mostly. One of the newest radios actually has the ability to download modulations. Can I change controls? Not until just very recently. Can I change features? Theoretically, and it's just now starting to happen. There's a few radios out there you can. Is it user programmable? Generally not. Is it software controlled? Absolutely. Half of you guys in the room are doing it. So this picture now represents software-defined radio as known in the last 10 years. One of the things I'll explain to you is virtually all of the SDRs that are out there all have this genesis in a piece of software called Power SDR that we did about 12 years ago, and so and gave it out to the industry in the hopes that this hobby might change. And guess what? It did. So this is what software-defined radio looks like. Well, what about the modulation? Well, it's expandable. That's a good sign. Can we change the control? Sure, you can move the volume control down. You can put the band switches over. You can do pretty much anything else. Can you change features? Yes. One of the cool parts about software-defined radio. Is it user programmable? Absolutely. In the case of Power SDR, it's open source. You can download the source code from us or any number of places and, you know, just go crazy making changes. And is it software controlled? Software-defined, software controlled. Yes. You can software control a software-defined radio. How many people use a contest logger, DM780, Mix W, Ham Radio Deluxe, all those other things to drive your radio? Well, guess what? All of that can drive any software-defined radio as well. So, time for the first disclaimer of the day. I hate to tell you this, I do work for FlexRadio. I also happen to be the VP of Sales. I promise this is not going to be a sales pitch, okay? No, I mean, because I'm a geek ham. But here's the disclaimer. I cannot do 55 minutes of a talk and not mention FlexRadio, because we started it and we're the kind of the 900-pound gorilla. But I will do the best I can to describe where the market and the industry is going, because I think it's pretty fascinating. Back to our regularly scheduled program. So what is a software-defined radio? Well, we in the ARRL and several others believe that this is the definition. Modulation using software, and it's changeable. Digital signal processing in software, or some sort of software-like device, like DSPs and things like that. The control surface is reconfigurable, meaning you can move things around, you can add new features or controls, and the radio can be controlled by software. So this is the SDR definition we'll be using. So, we did start it. Gerald Youngblood, our founder, about 12 years ago was sitting at his kitchen table and got this crazy idea that he might be able to take and move a piece of the radio into a PC. And he just kept moving more and more pieces into the radio, starting at the audio and working back. And when he got to the very first mixer, he said, wow, that's pretty good. Couldn't get RF into the radio quite then. So he wrote a series of articles. These are fascinating articles. I would recommend, if you're interested in the technology behind soft SDRs, read them. They're actually well written so that they're not dry. Yes, sir?
I have a question. I had a Pegasus well over 10 years ago.
Yes.
And that was sort of seemed to me to be an SDR type radio. How is that different than what was developed after?
So the Pegasus is actually a classic super heterodyne multi-conversion radio with DSP at the back end. And I'll actually show you a picture of that architecture here in a second. And so what they did was they bit off the last demod stage where the demodulator was in DSP. And so that's one of those gray areas. It's really challenging to decide whether that's an SDR or not. And believe me, there's no value in arguing those points. No, but it's very interesting because Pegasus is, I can't figure out how to get the word Tentec into Iko Kinye Woodcraft Tech. But I will one of these days. But they're there, absolutely. And they were one of the leaders, the early ons. By the way, no problem asking questions. I'm going to move fast, as you can tell. Just remember, my calculus professor said there are no stupid questions, only stupid people asking questions. What was yours again? No, please, if you've got a question, just ask, and I'll do my best to answer it. And I do have a place for questions in the back. So, let's talk about RF. Oh, you're a great straight guy. I forgot this was coming right up. We're going to talk about the basic RF architectures here. So we're going to talk about multi-conversion, aka super heterodyne. This is your car radio, your TV, any older scanner, Iko Kinye Woodcraft Tech radios. They are there, that they basically are represented, and I'll show some block diagrams of an input, some sort of mixer, some sort of filter, more amplifiers, more mixers, more filters, more amplifiers, and then this thing, this cloud. This cloud might be hardware, detector, demodulator, or it might actually be software, DSP, or any number of other things. But they are characterized by being multi-conversion. Direct conversion, how many people here have built a crystal radio? What do you remember about a crystal radio other than that it was hard to get something to work? Once you tuned it, the audio was amazing. That's the good news. Bad news is, man, there were images everywhere. And up until software came along, there was really no easy way to get rid of those images. That's why direct conversion receivers never took off. They were actually designed after the superhet in the early 30s. But they never could take off because you couldn't get rid of the noise. And then there's this new thing called direct sampling, where I'm just going to open my arms and go, radios, come to me, please. And we're going to capture that right into software. And we'll talk more about that at the end. So, here's that block diagram. And yes, I know it's backwards. Long story, too long to go into here. I'm not the best PowerPoint guy on the planet. I actually imported this from PowerPoint and I never could get it to flip over in Keynote. So, antenna through an amplifier, filters, there's the mixer. An LO, a local oscillator. A filter to get rid of half this because you get the sum of the differences and you get the sum and the difference of both frequencies. 7 megahertz and 1 megahertz come together. You're going to get 8 megahertz and 6 megahertz. I only care about half. I'm going to whack half of it off. Sounds perfect, doesn't it? Things aren't really actually as perfect as they sound, but that's the theory, okay? So then what we're going to do is we're going to go through here and we're going to filter out with a perfect filter, of course. And then we're going to add some gain and more gain. Wait, these have noise too. And another perfect filter. And then another mixer that's perfect with another LO that's perfectly on channel. And then there's this detector box, which, by the way, Tentec were really the first guys that figured out you could do this in software with a DSP. And then out to audio. And that's what it looks like. So what the Tentec folks did, and the military folks, is they did the same thing here. And they figured out that they could use digital signal processing and take care of that last stage and whack all that off. And I will tell you that in the last 10, 11, 12 years, all the high-end radios, the Tentecs, most of the military radios, all now use some form of digital signal processing to do that. Here's kind of an interesting funnel diagram of what it looks like. You've got the RF spectrum out there at the end. Then what we're going to do is we're going to neck it down to some intermediate frequency. In this case, this is a Pro 3, I think. 64,455 megahertz. It's sort of random, but there are some reasons for up converting versus down converting. I can't really get into that. Then we're going to convert it again to a very low frequency, and then we're going to detect it somehow. This one happens to use, again, an analog to digital converter and some sort of DSP. Remember when I talked about perfect filters and perfect mixers and perfect everything? Any engineers in here? Oh, good. Not very many. I'm in luck. Okay. When in engineering school, one of the classes they make you take is called thermodynamics. There are 3 laws of thermodynamics. They're really kind of complex. You can write all the equations, but they boil down to this. You can't win. You can't break even. And most days, you can't even come close. So reality says that every time I convert, or I do a mixer, or I do a filter, or I do anything that has a non-perfect, I love doing that, non-perfect, that won't show up on your camera, non-perfect lens, you'll end up with distortion. So these little boxes here are represented by distortion. Distortion is not our friend. Distortion ends up in your ears as intermodulation distortion. Oh, by the way, you can have intermod at RF, you can have intermod in the IF frequency, the intermediate frequencies, and you can have intermod in the audio frequencies. I've actually got some slides at the very end that we'll cover. So this one has 3 different stages of intermod. That, by the way, even ICOM, who they've been at it a really long time, they figured out from the 7800 to the 7600, let's get rid of some of those stages and have less distortion. In other words, the distortion caused by the IF stages is actually worse than doing multiple conversions. Maybe an idea for doing a direct conversion receiver. The other 2 things I want to show here is that one of the tricks is to put a roofing filter in the IF stage. Roofing filters. I can remember when they came on the scene and we thought we'd all died and gone to radio heaven. Guess what? They work awesome to get rid of the out-of-band signals. Guess what? Anything that's inside the roofing filter's passband is subjected to the same distortion and the same intermod. Rule number 2, you can't break even. The other thing I want to introduce here too is kind of a feel for how much data is flowing through here. In the Tintec and the later ICOMs and stuff, this data here is about roughly 100,000 packets of data every second. They call it kilosamples, or 96,000 samples per second of data if you were to capture this in there. So I just want to kind of give you a feel. Well, so what's good and bad? Well, in the multi-conversion world, adjacent band rejection is awesome. It really is wonderful. So they're great for harsh signal environments. It's a common, well-accepted design. Most of us that have been working on radios a while can actually open up a radio and work on it without a schematic, because you go, yeah, there's the first IF, there's the second, there's the filters. So you could, there are some problems, however, though. The only signals in the final IF can be tuned, so that means your bandwidth is narrow. Distortion introduced in each stage of the filter gets added to the next stage. So you have a limited view of spectrum, and then you really do need crystal filters, roofing filters, or some sort of filtering to narrow the out-of-band signals. So enter direct conversion, and this is modern direct conversion now. This isn't your crystal set, though it works perfectly the same. Antenna, low noise amplifier, filter, this thing called the Quadrature sampling decoder. Those 4 articles I was telling you about, go read them. Basically what it does is it samples the RF, uses a spinning wheel on frequency, and captures it at various points around the compass, stores those off, and you get these 2 streams of digital bits. And from those 2 streams, you can do anything you want. You can go from frequency to time, time to frequency. You can do all kinds of neat things. It's called I and Q. You'll hear a lot about IQ radios, LP pan, things like that. So this is where the I and Q come out. And then it goes into this cloud. That cloud can be software. The cloud can be software inside a chip. The cloud can be firmware, DSP, and out pops audio. But this is the current modern direct conversion receiver. It looks like this in the funnel diagram. Guess what? There's still distortion, but there's just distortion in one place. Right there, the one and only mixer. But it's there. It's not as bad, but you have to acknowledge it. The other thing is, it takes about twice the amount of data to handle this. So now I hope you guys see a train wreck coming. Because if we're going to do software-defined radio, I got to handle this data somehow. The cool part, though, is when I get to the DSP here, I could do things like multiple detectors. I could put a couple of receivers in there, listen on 2 places, as long as it's inside this bandwidth here, because this bandwidth went from 36 to 192. I can listen to the entire sideband section on 20 meters in one radio at the same time. So I can do that. I can also add visual things like pan adapters and displays.
Question?
Yes?
Thank you. So it's clear there's much more flexibility, but the distortion argument seems one-sided. So you've got an ADC, your Quadrature mixer, and then a couple of ADCs, which have quantization noise.
Absolutely.
Which is much bigger, since you have to deal with this huge dynamic range before any AJC circuitry, right?
Yes,
I
but
think that would more than make up for the.
So now I'm going to cheat and tell you that what we do is we mix this down to a 15 kilohertz IF and use amazing high precision audio ADCs, and you're running 24 bits, and so you get, you can get dynamic ranges of 100 dB with designs like this. It's being done every day, so that's how you get away with it. So there is distortion in the QSDs, the Quadrature sampling decoder, but it passes right through, by the way. So what you do is you do tricks like image rejection in software, AGC, and things like that on software. You do deal with it some, but it's there and it does exist. But typically the
overall, you think you really come out with a
yeah, absolutely. The proof is in the receiving, because these are amazingly quiet receivers, amazingly. So and this is what a block diagram. I want to push this IQ thing one more time. You come through here, you do a Quadrature sampling detection, and this ends up at about hyper audio ranges. Use 2 op amps or something equivalent, and then you pump it right into a sound card. There are literally things. Anybody played with a soft rock? It's great. It's got 4 capacitors in it. That's what it uses as the QSD charge pump, and 2 op amps. You hook up the 4 caps to I and Q, you play it into your sound card, and ta-da! Works great. Third law of thermodynamics. Most days you don't even come close. You're now subject to the vagaries of your PC and your sound card and all the wires and the hums and everything else. Yes?
Yeah, just for listening, I have an RF space SDR IQ. Is that essentially what this is?
The SDR IQ is actually direct sampling. We'll get to that.
Oh, okay.
Okay. So, but there's obviously more circuitry underneath here that it takes to drive these things. But the fundamentals are that it's basically just charging up 4 capacitors going around this circle and running it into a sound card. So we learned early on, by the way, though, that letting other people use their sound card was a bad thing. Our first radio actually used a sound, we played it out to a sound card, and then we had a problem with everybody's sound card giving us problems. The good news is that the distortion's minimized. There's only 1 mixer, so you get better clear. You can actually see up to 192, almost 200 kilohertz to the display. It's a low power, high dynamic range design. It's very good. By the way, image rejection is a real problem. You have to get a very good balanced IQ device, that quadrature sampling, and then you have to pull software tricks like wideband image rejection, things like that. So, and it's better as far as view, but it's not perfect.
Another question?
Yes?
So sensitivity, since you have all this out-of-band energy that your ADCs have to handle, even if you have 24 bits, how does sensitivity compare to superhead?
There's a actually, MDS is really not a problem at all. One of the things I'm going to tell you down the road is that every modern radio hears way better than it needs to now. So sensitivity in the HF spectrum just isn't an issue anymore. You can hear much better. Now what you have to worry about, though, is sensitivity at the noise floor. And there's pre-ADS. You treat it. You do some filtering, but it's very minimal filtering because the filters will create distortion. So you do minimize it, but it really isn't an issue on these. Like I said, these things are at least as sensitive as every other radio, and they're quieter. So. Oh no, these things will hear. You know, we make one that has a 4 dB noise figure. So on 6 meters, which is pretty decent. This is actually where it all got started. If you want, we could talk offline. I'm afraid we're going to get too deep into it if we don't. This is actually the first SDR 1000. This is what they built, a few thousand of these things. And you can recognize parts. This is an antenna tuner. This is filters. There's PA section. So guess what? Has a lot of radio parts in it. It also has a board in it that does all that magic and then shoots it out to your sound card. We learned right away that shooting it to your sound card was not a good idea. This is that soft rock. Guess what? There are those 4 capacitors right there. So same circuit. This was a $20 design that Tony Parks did and sold bajillion of them. So probably lost money on every single one of them. But it's the same design. So then we came off and we did one where we moved the radio or moved the sound card inside. This has been insanely successful. We shrank them. This is not a sales pitch, so I'm just ripping through these. We even made a QRP radio. The key to this was actually the software. This Power SDR software that has become the basis of everyone. And so it allows you to see a big display. It allows you to have lots of buttons. By the way, this is both the blessing and the curse. That's a lot of buttons to have to look like. There's lots of distortion in the buttons. In other words, holy cow, what do I do with all this data?
Question?
Yeah.
Can you put that on a touchscreen computer?
Absolutely. You bet. Runs great. I have comm trailers in Texas that I help support where they've got the big 60-inch touch screens for doing GIS mapping and stuff. And we'll pop the radio up there and drive them that way and pan and zoom. It works very well. Basically Windows has finally got touchscreen down pretty well. So what's happened though is in the last few years, direct sampling has happened, SDRIQ, things like that, where we come in through an amplifier and some sort of minimal filtering, and then we just catch everything. Nirvana says we've got a chip and the 50 ohm connector right to it, and we play it right in. Oh, if it was only that easy. The bad news is there's aliasing and there's overload and there's the FM broadcast station down the street and everything else. But the cool part is when you're done, you squirt out either real or I and Q data and everything else is done in software. And you can do all kinds of cool things with it. But the bad news is you've got to capture more data. There's this guy Nyquist who had the audacity to think up this theorem that said you have to actually sample more than you want to capture. So you have to capture a lot of data, like 250 megahertz worth of it. You got to have an expensive A to D and do a ton of DSP on it. And oh, by the way, you really still have to create an IF, but it's all in software at that point. So there are mixers. They're just perfect mixers, plus or minus the quantization of the mathematics inside of the digital signal processing. The neat thing is, though, now all of a sudden I can have lots of detectors, lots of pan adapters, lots of serial data, 8-band skimmers for CW watching 35 PSK signals at once while talking to your buddies on 80 meters, all at the same time. No free lunch. I now have to sample at 250 million samples a second. So we've gone from 36 kilosamples, 96, 192, now to 250 million. This is a big problem. Distortion is crazy good, wonderful stuff. And you have the ability to create N receivers and N pan adapters, varying widths, more bands, more receivers. Very, very high dynamic range, higher than anything else in terms of a traditional radio that's out there. Extreme flexibility. The bad news is it's technically challenging to design. Yes?
Very wide dynamic range. Number?
Better than 105, IMD DR3s.
Okay.
And BDRs, blocking dynamic range is simply not a meaningful number anymore. If I told you I could take a plus 17 signal without overload, and I can hear MDS at minus 147, then plus the processing gain, I can actually get below the noise floor another 10 dB. What does 160 dB mean to, I mean, you know, it's not meaningful anymore. It's crazy wide dynamic range now, and that's the good news. So.
It's ADC resolution? How else would you get?
No, you do decimation gain. You do it in the DSP. Okay. Yeah, no, the ADCs are good, but they're not that good. Yeah. Okay, so the guys from Tapper, started this group called Open HPSDR. We actually sponsored their website for a long time, and they built this box several years ago. It's a kit. Any Open HPSDR guys here? Great. What a wonderful project. One of the guys that works for us built a couple of the boards on the team and things like that. This is true ham radio advancing the state of the radio art. Very cool, kind of pricey, but it's neat. You can build one of these things yourself. We actually did work for the government about 5 years ago now. The bad news is, and it does wonderful things. This one does 16 receivers, fits into a PC, had better than 90 dB of wideband, spurious-free dynamic range. That's a term you'll hear, SFDR. Goes up to 140 megahertz of bandwidth. The bad news is, underneath this fan was a $6,000 component. Not quite ham radio yet. So we had a problem. Now all of a sudden we're looking at how to do design. And there's this argument. You can go with an ADC, this analog to digital converter, and a great big pipe, a hose. And you can use this thing called the field programmable gate array. I'll explain some of that in a minute. And then squirt it all out to PC, and we could continue to use Power SDR. All would be life, life would be good. We've got 10-year investment in software. It's wonderful. Minimal software investment. All the work would be done in the FPGA. That's one way to do it. And people are doing that. Lots of DSP power in the computer. It's easy. It's ubiquitous. Plenty of PCs, plenty of people. Bad news is you got to have a PC on all the time. And to control it remotely, you're going to have to use VNC, go to my PC, log me in, those sort of things. Audio is going to have to come via Skype. So it's going to be like what we're doing now in the software-defined radio world. It's hard and not particularly bandwidth friendly. I'll show you some pictures in a minute. So, by the way, we've done this for a while. In 2008, we built 32 Flex 5000s in a rack for our rich uncle Sam. And they love this, but it takes 2 gigabit Ethernets to capture all the data. Here's one we did a couple of years ago that'll do 24 80 megahertz wide analog to digital converters. It takes 4 10 gigabit fiber optic cables to catch the data. How many people have 10 gig Ethernet in their shack? So we got a problem here somehow, and this is a big deal. Okay, so some of the direct sampling radios that are out there, I talked about HP SDR. SDR IQ's in this family right here, okay? And the Anon 100, Hermes, but these are, you'll hear people talk sometimes about them as being fat pipe radios. Yes?
Can you comment on what they're doing with that much spectrum? I mean, on the soft, I mean, not just...
Oh, you mean the other guys?
Yeah.
No. I don't know. See, that's the best part. I don't know. I'm shipping them INQ data, and what they do with it, that's their job. So the other way to go about doing this is to do the same analog to digital conversion through this field programmable gate array to chew up all the DSP stuff, and then you're going to have to do, oh, this is baseband processing, digital signal processing, logic, and things like that. But then you end up with this nice little skinny pipe out to your PC or some other device. Okay, so the radio reduces the bandwidth before you get to the Ethernet, but oh man, we're going to have to boil the ocean and start over on a 10-year investment of software. That, by the way, thank goodness we're a bootstrap self-owned company, because no investor in their right mind would go, "You're crazy, we never do that." But what did we know? So basically what you have to do is you break it up into this thing, this FPGA. You've got to do a lot of digital signal processing, and you even have to do all the mic and speaker signal processing. So you break it up into chunks that way. That is one of the ways we've gone. A couple other people are going that way. We pulled all of that heavy thinking into the box and created a radio that's out there. Again, sales stuff, go talk to me in the booth later. But you can actually run this thing without a local computer. The key to running the baseband processor inside is that you get consistent performance independent of the PC. I joked earlier somebody that I said, we spent 10 years selling first a third of the radio, sound card, PC. Then we sold radio, and you had to buy a PC, and we had to support, by the way. So we only made money on half of the system, and we had to support the whole system. So now we've got everything in the box, and it'll run off of any PC, any IA, whatever thing. You know, that makes our job easier. I mean, we've been in business long enough to know that we have to stay in business somehow. So we minimize the network bandwidth, we minimize the system level problems, and it's self-contained. And that really is a big deal. Plus, all this spectrum display that everybody likes to see is now independent of available bandwidth. In other words, here's an issue where this is power SDR, and we know a lot about it. If you want to display 1 megahertz of bandwidth, it takes 77 megabits of network process. Here, if you want to display 1 megahertz of bandwidth, it takes 500,000 bits. 500 kilobits, 77 megabits. It's 150 to 1 bandwidth usage. If I go to 10 megahertz, I'm now 1500 to 1. So I can run this on a Wi-Fi over a 3G network. Keep that in mind. That's an important thing. Real briefly, this is what the architecture of a typical direct sampled radio would look like. You have the ADC, this field programmable gate array. Think of that as programmable hardware. That's really what it is. It's programmable hardware that we can actually change on the fly. You want to be CW? Here, be a really good CW radio. You want to be sideband? Here, be a sideband radio. And then it takes processing and digital signal processing, and there's supervisory things. And it even takes special coder, decoder, to do mic, speakers, headphones. So really the only time that your audio is analog is right at the connectors of this radio. Everywhere else it's all digital, and that's the key. So this is a block diagram here. You have these things called spectral capture units that grab all this data. By the way, they're still filters, and they do leak and those sort of things. You've got preamplifiers and attenuators. You've got analog to digital converters. You've got this big block of thinking that happens right here, and then it spits it out to an Ethernet port. The interesting thing is we keep talking about data. Guess what? By the time it gets to this block of data, we're now dealing with 8 billion bits of data a second. 8 gigabits. And so it's tough. It's a lot of data. That's probably the biggest challenge. So what kind of processing does it take? Ooh. Okay, anybody remember the Cray? It ran 80 billion floating point instructions a second. Well, then that's okay, because then they built the Cray 2 and it was awesome, because it went to 4 billion instructions a second. And it was only $4 million of, here's a term, gigaflop. That's 1 billion floating point instructions per second. That's a lot of calculator math, okay? That's everybody in the room gets a calculator, everybody in San Jose gets a calculator, and we all add it up and get an answer. It's expensive, but it works. By the way, the Cray X1, just for picture, it did 205 billion floating point instructions a second. It was cheap, $2.5 million bucks, about $12,000 a gigaflop. So what does this mean in terms of ham radio? Well, most of the ICO Kinye woodcrafts 10 years ago had about 120 million floating points. This is a Pegasus class, early class radios were in that area. So then what happened is there was this big break, and all of a sudden the DSP radios hit the market. And they were 10 times faster. There's another term here called a multiply and accumulate. It turns out that in DSP, and what I know about DSP, you can put in a thimble. I'm an RF guy. But the fact is, if I did give everybody a calculator and I had everybody on this row, you add up, you multiply numbers, you guys multiply, and then you pass your data. You guys down here, you each add them up and then hand me the answer. That's a multiply and accumulate instruction. It works, it's really quite simple. You just have to do it very, very fast. So then what happened is there was another 4x jump about 7 or 8 years ago. So now we're up to about 5 billion instructions a second. And then there was some, made it cheaper, basically, was what happened there. But the problem is, in order to do in-the-box direct sampling, it takes more data. As a matter of fact, the most we could get out of the DSP was about 14 billion floating point instructions and about 9 billion instructions a second. That's not fast enough. You really need something on the order of about 80 billion instructions a second and about 150 billion multiply and accumulates a second. So it takes this device, this programmable hardware thing called an FPGA, and trust me, all direct sampled radios are going to see those pop in there. And our biggest radio that does up to 8 receivers, just for completeness, takes like 300 billion instructions a second. That's the processing power inside the radio. And so, you know, hey, we're cheaper than a Cray X2 at about 60 bucks a gigaflop. Well, look at it this way. Yes?
How would that sort of number of operations per second compare to like a mainstream PC CPU or mainstream PC?
You know, I've been asked that question many times, and the best answer I've been told is that they'll do on the order of about 30 to 40, but I have not gone back and done the math to prove that answer. If there's somebody here that knows that answer.
So even because it is specialized DSP hardware, you're able to get?
Yes, yeah, we're cheating. It's physics, we're just cheating. We're running programmable hardware. It's everybody in the room doing math at one time. You bet. So why do we do this? Obviously many pan adapters, many receivers, doing the DMOD and things like that, one antenna, advanced DSP functions. But this is the guy, and we happen to use this company, Vertex. They're right here in Silicon Valley. They're the big dogs, and we've been with them for a long time. But basically it allows you to do this DSP in real time. It's 90%, by the way, of the power is in here, 90%. Okay, here comes 2 minutes of DSP. You ready? Goal number 1, we want to convert things captured with an A to D into audio so you can hear them. We want to convert those same signals into some visual representation so you can see them. Guess what? It turns out that you have to do that in 2 different ways simultaneously and make them synchronized so that they don't make you sick looking at them. So the trick is these things called digital filters and this wonderful math program called fast Fourier transform. By the way, it's all everybody with the calculator, add them up, shoot them down the aisle, drop them in a bucket, get you the answer. It all uses a very, very simple set of math that you do over and over again. And this is what it looks like. You come in through the analog to digital converter 245 million times a second, and then you add all these data together. This thing called, you have basically, it's real simple. This is a multiplier, and this is an accumulator with coefficients, and then you add it all together so you get multiply and accumulation. Ta-da, you're done. Now all I have to do is just do that a whole bunch of times. You could do it in software. Here's your software answer. And you do it as a loop. And it looks like this in software, where ultimately you end up with one equation that you just do over and over and over and over again. Okay? So the problem is that on a 1 gigahertz digital signal processor, you can only do about 8 million of these a second. That's not fast enough. So then what you do is you start spreading out. That would be like you doing the math. Now I'm going to have everybody do the math, and here's how we're going to do it. First, I'm going to have every row do it, and then that gets me about 20 times. Then I'm going to have every row do math again, and that makes it much faster. Now I'm talking about 600 million instructions a second just in the chip. And so it's real simple. It's a matrix of calculators running in real time to do the math. Okay, networking. I wanted to get to this. I was really rushing here. All right, there are those of us in this room that this number might be the 70s. And a few of you that might be the 60s, but I've been told that if you were from the 60s, what is it? If you say you were from the 60s, then you probably weren't there, because if you really were, you wouldn't have remembered it. So, but this is really true. I mean, this is what you used to do at a rock concert. Now this is what you do at a rock concert. How many people here have an IA kind of thingamabob with them? Some sort of widget. Yeah, right. Guess what? The numbers are just crazy. It's interesting. You know, you start looking at what's happening. I mean, those of us curmudgeons that actually got onto Facebook, I got on for business for the company, and I actually used to keep up with my cousin. Now there's things called Instagram and Snapshot and Flickr, and man, they're making new process, you know, data. It's all about data. The network is all about data now. As a matter of fact, if you look at the growth is in global mobile data, and it keeps growing year on year. And it's just crazy how much, you know, the year-on-year growth. It's 1.5 times per year right now is the way the data is growing. This is really interesting. Look at the growth from iPods to iPhones to iPads, just from Apple. And they're no longer 100% of the market. They're just a piece of the market. But it's crazy how big this business has occurred. All right, how many people? Come on, cough it up. How many people have an I or an A or one of those pad things? Yes. You ready? That number is now 33%. 33% of us adults carry around some sort of reader device. Okay, here's the last. How many people still get their newspaper at home? Wow. So I'm curious. How many are gerbils and how many of them are parakeet? Because there really can't be much other reason to use the print anymore. Oh, okay, training puppies. But the fact is that the advertising revenues have basically bankrupted the newspapers because it's all gone online. This is just a neat metric. In emerging countries, mobile data has actually surpassed internet data. Here's one of Chinese that's kind of neat. I mean, look at the uptick rate. You know, there are less people that have desktop PCs than have mobile devices now. And this is especially true in emerging third world, or, you know, China's obviously not a third world country, but their growth of technology is happening so fast. They've completely bypassed the wire. They've unconnected the wire completely and they've gone wireless. So what? Who cares? We're talking about this in ham radio. Why do we care? Well, we believe that networking is part of the future of ham radio. And because of that, we think bandwidth is important. And we think running, not running away from your transceiver, but running apart from your transceiver is important. In other words, we're all mobile folks. We want to be able to, get away from our shack. All right, here comes. Any DXCC types in here? I see a few of you I recognize. Okay, I'm at my QTH and I work Christmas Island, Tango 32 Charlie. I get to put it in the log, right? The XCC says, yes, that's a Q. So, I send the guy an email. Hey, how's it going out on the island? Good, great. Okay, put me in the log. Wonderful. Is that a Q? No. So we've kind of established the boundaries, right? One's purely RF and one of them's purely bits. And so we know where ham radio is. Radio's over here, chatting is over here. Okay? Now it gets blurry. You grab up your 2-meter handheld, your wax on, wax off, and you talk to Christmas Island via the local Echolink node. And magically, they have an Echolink node on their island as well, even though it's uninhabited. But you transmit there, and you talk to the guy and say, hey, 599, 599, it's great. Do I get to count that one? No, because it's mostly internet. But I'm at the grocery store. I get a text from one of the guys, the guys I microwave with. TEP is open. For those of you who are not into 6 meters, transequatorial propagation is something that those of us in the middle part of the United States get to enjoy. I worked Chile and Buenos Aires this week on TEP. Actually, I got to show a kid his first TEP cue this week. It was awesome. So I get a text that says, TEP is open. So I whip out my iPad. I log into to my shack at home. And I work them. Is that a cue? Yeah. Yes, it is. Because we're using my radios and my antennas and my tower, but I'm using a little bit of technology to get there. So we think that most radios should have one of these somehow. That's an Ethernet connector, by the way. So the question is, does your radio end up, oops, sorry. Nothing like cute art, got to do artsy schwartsy stuff and then it disappears on you, sorry. But we think this is where your radio should appear, or at least have the opportunity to appear. By the way, it works the other way. You could go to Tango 32 Charlie and you could put the receivers here, the antennas for the transmitters, or the low band stuff working JAs, and you could sit in the relative comfort of the huts that are in the middle of the island where it's 12 feet off the deal. Actually, I wish I had a picture of Clipperton, because the Clipperton guys, the only palm trees on the island is where the HF station was, and poor Lance, W7GJ, was like 1,200 feet away on this stone of bird poop running the moonbound station. So, wouldn't it have been nice if he could have just stretched a piece of fiber or a little quick microwave shot? So the real question then becomes, where does your operating position be? Is it here or is it here? And we think there's a reason for both. We really do. But there's that bandwidth thing. This is a great example. This is a current existing deal using a direct conversion radio, one of ours or anybody else's for this days. Even the direct sampling radios with the narrow DSP where they've got to talk, you've got about 100 megabits a second of data going between your radio and your PC, but then somehow or another you've got to get that data to your iThing, where that's probably only going to be a half a megabit, a megabit, a 3G LTE is 3 to 5 megabits per second, so that's precious bandwidth. So the DSP can be, where does the DSP get done? But the real question is, forget about all that bits and stuff. Have you ever missed a DXQ because you weren't at home or you were too busy, or, oh crud, sorry, I'm kind of out of whack here. You're too busy, your station was restricted, you had unfavorable weather. Those are things to think about. So the other so what is, how good are these radios? Well, this is a chart that Rob Sherwood from Sherwood Engineer presents, and I covered up the other guys. I will just tell you that arguably these are several of the very best radios on the planet. You remember I was talking about that intermodulation distortion in your head? This is what it looks like when it comes out of your headphones. These are very high Q filters. This one has an 8-pole crystal roofing filter in it. There's the 2 tones for the test. Same 2 tones, by the way, here and here and here. But all of those multi-conversion stages start doing this. And then the then the intermod from the first stage ends up mixing in band with the intermod from the second stage. And so you end up with spurs. And guess what that ends up as after 12 hours of contesting on the 160 meter CQ or CW contest? Fatigue as you throw your headphones out the window or your radio. So this is probably the best quantification of that fatigue that I've ever seen. The guys in Russia did this, and that's why I show this chart. It's very cool. The other thing you get is just killer filters in because they're software. You can do them in software. These, I will tell you that this one is this is kind of a neat chart because these are sort of the progression. This one happens to be are software only. This is a software in DSP, back in a la Pegasus, latest and greatest radios. This is a hybrid of hardware and software, and this is a mostly hardware solution filter. And that's a sideband filter that was done. And these are actual plots. This is what the 500 hertz brick wall filter looks like in software. I mean, that's the physical plot of it as after it's been rendered in software. That's pretty clean. In other words, you can go from, you know, you can have 100 dB of dynamic range in getting rid of your out-of-band signaling. That's very cool. If you're a CW guy, these are wonderful filters. Come by the booth, I'll show you what a 10 hertz filter sounds like. With no ringing, by the way, because you just take the ringing out in software. There's what a sideband filter looks like. Again, brick wall. You ever had that guy in your 40-meter queue that, you know, Thursday night that always shows up, and he always shows up about this close to your deal, and you just reach over and grab the edge and you just whack him. You just take him out. That's what software-defined radio is cool for. I had talked a little bit about radio's minimum discernible signal, and this is a really nice chart. This would apply to everyone. As a matter of fact, the ITU did this chart back in the 60s, and these lines are urban, rural, and quiet rural. We joke about the fact that this is Rob Sherwood's shack out in Colorado because we don't know anybody else that's that quiet. But it does exist. So now what you do is you start looking at how quiet do you have to be in order to be better than this. And so you plot minimum discernible signal versus frequency. Now, here's one other little piece of data I'm going to show you. This is 160 meters. If you live in an urban area and your S meter is not telling you you have an S8 signal, most of the time, your S meter's lying to you. Which is what most of the ICO Kinye would craft, not tech. They do an excellent job keeping their S meters right. But this is one of the quirks that you know, it's like you want the truth, you can't handle the truth. So all the Japanese folks just lie to you, and the meters just lie. They're accurate at S9 and they're accurate at, you know, 60/9 and nothing in between. So you should check, if you ever get around a signal generator, dial in -73 and see what the S meter says. It should say S9. And then go down 10 dB and see if it says, or go down 6 dB and see if it says S8. So the deal is that the environmental noise in your shack should show up on your S meter, okay? If it's not, basically your S meter's lying to you. So the other part of this chart is that you only have to make radios that hear about -120, you know, S2 or 3. So if you could build it down here, then you cover most of it except on 12 meters, 10 meters, and above. The other message here is that for a really good radio with wide dynamic range and high performance, you should never have to turn your preamps on until you get to 10 meters. As a matter of fact, if you don't get an 8 dB improvement in signal to noise, turn them back off. Or, corollary-wise, turn your attenuator on if you're trying to run 160 or 80. You'll get a better signal out. And so, quit thinking about, you know, your 599, good luck in the contest. The guy on the other end's going to lie to you and tell you got a 5.9 anyway. So, you're 5-1 in your Q5 copy. It's great. I've got you 6 dB out of the noise in your perfect copy. It doesn't matter anymore. And so this is sort of one of those great myths of ham radio that's been kind of difficult to get people to undo. Some of the other things you can do is you can create really neat things like RF tracking notch filters. Everybody have an A and F filter in their rig, right? You push it on, the tone goes away. What happens if you have 2 tones or 20 tones? So this was an argument in our shack. I kept having customers tell me, I want more filters. Well, how many do you want? Well, how many can I have? Well, how many do you want? How many can you have? So I'd go back to the staff meeting and Steve, my VP of engineering, be like, Steve, I need more filters. Well, how many do you want? How many can I have? How many do you want? How many can I have? So he walks in one day and he goes, how does infinite sound? Ooh, infinite's good. So the guys developed this thing called an RF tracking notch filter that basically camps out. You can set the width, you can set the height, you can set everything out, and then forget it. Imagine sitting down with your cold favorite beverage on an evening and taking out every foreign broadcast carrier in the 40-meter band. Forever. They're just gone. I mean, oh, they're there, you can see them, but you'll never hear them. So you can build multiples and you can tune them, and they're tracking via RF, not into the audio passband anymore, so they're memorized. The other cool thing you can do, this is a huge dig. I will tell you that we're really proud of the fact that we have awesome QSK performance CW, finally, on a software-defined radio. Anybody that's ever done software-defined radios knows that the problem is you go DIT, it goes through your radio, down to the PC, gets processed, comes back to your headphone 60 to 80 milliseconds later as a DIT, and your hand just freaks out. It turns out you're affecting the same part of your brain that happens when you eat bad berries. So if you have jitter, now you get vertigo and throw up. So it's the same reaction. This is one of the biggest digs against software-defined radio for the last 10 years. So one of the cool side effects of bringing all the DSP and stuff back in the radio is we get CW that's just as good now as Aiko Kinye would craft tech. So the deal is that this was a big problem for CW operators on software-defined radios, and we've overcome it. This is an 8 millisecond key-up delay, by the way. That's the classic ARRL test. Great dynamic range. This is a wonderful. The reason we're not quoting exact numbers is because the ARRL and Sherwood haven't published their numbers, and there's sort of this thing in the industry where you let the other people brag about the numbers, and then you go, yeah, we're that good. But I can show you that these are two S9 plus 73 signals. These are 0 dBm signals. If you want to see a cool real-world example, the special event station on our radio is minus 18. And so 15 kilohertz away, I can copy people in the noise with no filters on an antenna. But anyway, that's a pair of signals that's running about a plus 51 IP3 for all you RF guys. These are big signals. So what's left? Well, just making it simple. Any pilots in here? I have an old 172. This terrifies me. This is the picture I always hate to look at. There's way too many gauges in here. This is what most people think Power SDR looks like, by the way. So what you really want is this. You want the latest and greatest. You want it to be clean and clear. The 7087 is a wonderful airplane, except for the lithium battery that explodes. But the neat thing is that all of a sudden you get, just the stuff you need. Bing bong, you're a little too low. Bing bong, 6 meters is open. Bing bong, your lithium battery's on fire. But this is the kind of stuff you want. So what you want is some sort of clear. This is the other big dig on software-defined radio, is how to make this cleaner. So we've been working, and we hope other people, there's some other programs out there, some guys in Europe are writing some really cool SDR front ends, and we're excited about that. The whole industry is trying to figure out a cleaner, clearer way. This introduces a thing called the concept of the slice. This is a slice receiver. That's an independent receiver. Oh yeah, it's all in software and there's no real components, but that's a slice receiver. And it has all its own things. Here's another slice. These are pan adapters. They are chunks of the spectrum that you can see. So this pan adapter has its own controls that pop out when you need them. Bing bong, time to change bands. And so otherwise, things are very clean and clear. Why is that important? Well, what happens when I go to 4 of them? This is 4 displays running on 10 meters, 12 meters, 17 meters, and 20 meters. By the way, these radios will do 4 or 8 bands simultaneously. So you got to figure out a way to display all this data somehow, especially when you go to 8. Now all of a sudden you're looking at a lot of data. That's, I think, all 8 of the close ham bands there. But that's a real problem that you've got to cope with, and it's got to get smaller and it's got to get cleaner. The other neat thing is you want to be able to move them around and adjust them so you can do this. Once again, this is Greg watching for some 6-meter opening. I noticed that these guys were starting to get TEP, and I thought, if it would just move over. That night it got as far. XE2OR, he's got a killer signal down in Monterey. He started working it and never got into Texas though. Darn. But you'll notice what I'm doing here is I'm looking at all of the windows. I'm on the 6-meter international 2 frequencies. I'm looking on the classic 50.125. And oh, by the way, I'm working somebody on 24902 on 12 meters while I'm just killing time waiting for the band to open up. So, we think the vision is that we're on vacation, we're at the beach, we're running some obscure new digital mode that we just got to invent and shove down into our radio from an iPad and talking to a DX station. And it's no big deal because we want it so that everybody can do this. So, you know, what could you do with 4, 6, or 8 receivers? What could you do with the ability to directly decode and display digital modes right from your radio? The ability to transmit locally and listen to yourself remotely. The ultimate in narcissism. It's what it's all about. It's great. Hello, hello. So, access to remote databases on the internet while, you know, tied into your radio. And then a radio appliance that can be connected via Ethernet to any computer. So the concept of a radio architecture. I'm going to stop here because it will, from here on out, it'll get into sales, and I don't want to do that. Come see us at the booth.